In our previous classes, we have discussed about the mapping between S-plane and Z-plane in the how we map all the values of S-plane into the Z-plane, and we have discussed how it is being mapped by the equation Z is equal to e power Ts, and what are the various loci that are existing in this constant damping ratio loci, the constant frequency loci, and the constant attenuation loci. In all these things, we have understood that where in the S plane and the Z plane, for example, in the S plane and in the Z plane, what is the difference between these two? Now this is sigma and j omega axis, and this is real part of Z and imaginary part of Z. This is our Z plane. Right. In these two, what we have understood from the previous class is all the poles that are lying on the left half of S plane, which means that they are giving a stable, this is a stable region, are mapped onto the inner part of the unit circle or the inside of the unit circle, and those poles and zeros on the imaginary axis of the S plane will be mapped onto the unit circle, and all those which are lying on the outside of the unit circle, which contribute to the unstable behavior of the response, that those values of poles and zeros will be mapped onto the outside of the unit circle, is what we have discussed in the previous class in the mapping between S plane and Z plane. Now today we will be studying about the stability analysis in the closed loop system, stability analysis in the closed loop system in the Z plane. For example, what is a closed loop system? Let me say we are having a plant G of Z, and without using any sampler, we are trying to give a system like this, H of Z and C of Z here, right? And we have a negative feedback here, and obviously we know that the transfer function of this is C of Z by R of Z is equal to G of Z by 1 plus G into H of Z, right? Because there is no sampler, we can directly multiply the product of G of Z into H of Z. Product of G of Z into H of Z is equal to GH of Z. As we have discussed in our previous classes, this combination of these two polynomials will be giving us GH of Z. Now in this, to understand stability or to analyze stability of this closed loop system, of any closed loop system, we need to understand the location of poles and zeros, like in our S plane analysis. In our S plane analysis, what is it? We are considering the denominator polynomial. We are considering the denominator polynomial and equating it to 0. What is that denominator polynomial for us here? 1 plus G H of Z. So this can be termed as the characteristic equation, because the location of poles and zeros of this characteristic equation will be telling us whether the system is stable, limitedly stable, or unstable system. Therefore, the poles and zeros of this, the location of poles and zeros of this characteristic equation plays a pivotal role in determining the stability. That is what we are trying to understand, stability analysis. Whenever we say stability analysis of a closed loop system in a given plane, be it S plane or Z plane or any other plane, even we have W plane, right? Anywhere we need to understand that the characteristic equation is the most important role, plays a very important role. And P of Z is equal to 0, 1 plus GH of Z, as derived from this block diagram. You can say that this will give us very vital information about the poles and zeros, the location of poles and zeros in the Z plane, because the domain is Z plane here, right? So we are going to concentrate on P of Z is equal to 0 in this lecture of ours. So P of Z, which is nothing but, and to remind you all, we will be discussing only linear, time invariant, single input, single output, discrete time control systems. We will be discussing only this type of system here. We will restrict ourselves to this type of systems: linear time invariant, single input, single output, and discrete time control systems, for which we are having the characteristic equation P of Z. Characteristic equation P of Z is equal to 1 plus G H of Z is equal to 0. Now this is a closed loop characteristic equation, therefore the closed loop poles are roots of the characteristic equation. Roots of the characteristic equation. The location of these, the location of closed loop poles are roots of the characteristic equation. Now this characteristic equation P of Z, as you can write it in polynomial in Z, you can write it as A0 Z power n, A1 Z power n minus 1, A2 Z power n minus 2, plus so on, plus an minus 1 Z plus an, which is equal to 0. Right. So the characteristic equation can be considered in this form. It is a polynomial in Z. Right. So you can get the roots of this equation. And if you can map all those roots, and if you can place or locate all these roots, which are also called the closed loop poles and zeros, closed loop poles of the characteristic equation. And the important point here in Z plane is the unit circle. This is our unit circle. And this unit circle, if all the roots, how many roots we will have in this? You will have n roots. If all the n roots are lying inside the unit circle, then the system is stable. Right. That is, let us say you have Z1, Z2, so on, Zn are the n roots of the characteristic equation P of Z equal to 0. N roots of characteristic equation P of Z is equal to 0 are Z1, Z2, so on, Zn. And if mod Z1, you can say if mod Z1, mod Z2, mod Zn are all less than 1, then the system is stable. Because in our previous class, when we were mapping S-plane poles and zeros, S-plane points into the Z-plane, by the help of equation Z is equal to e power Ts, we have understood that all the poles of all the values that are lying on the left half of S-plane, all the values that are lying on the left half of S-plane are being mapped onto the inside of the unit circle. Therefore, this is a stable region, we can also directly assume that all the values that are lying inside the unit circle are zeros. Now there is another case. This is case 1. Now we have another case here, case 2, where if mod Z is equal to 1, that is, the poles that are lying on the imaginary axis of the S-plane. Right, mod Z is equal to 1. Right, so if mod Z is equal to 1, then such poles, if there is any one pole that is on the imaginary axis, then it is critically stable. Then the system is critically stable. What is the meaning of mod Z is equal to 1? The value is equal to 1. That is, the pole is lying on the unit circle. Since the pole is lying on the unit circle, we can say that mod Z is equal to 1. And any pole that is lying on the unit circle is giving us critically stable system. Now the case 3, if there is any pole mod Z greater than 1, any single pole that is greater than 1, the magnitude of Z is greater than 1, then the system is unstable system. And the system is unstable system. For example, in the case 4 section, what if there is any pole which is mod z is equal to 1 and mod z2 is equal to 1. That is a multiple pole. Any multiple pole is lying on the imaginary axis, then again the system is unstable. Multiple pole. If any single pole, here if you have any single pole on the imaginary axis, right, or lying on the unit circle of the z plane, then it is critically stable. But if there is any multiple pole, that is two poles are lying on the imaginary axis of the unit circle, then the system is said to be unstable. So with this in mind, we will try to understand what are the various methods. With this just location of poles and zeros, poles in the z plane will give us stable system. Right. In the previous class itself, we have discussed that the poles that are lying inside the unit circle are giving us stable system. Poles that are lying on the unit circle are giving us critically stable or limitedly stable or marginally stable system. And the poles that are lying outside the unit circle, that is mod z is greater than 1, you can say they are said to be giving us unstable system. Right. Or the poles are said to be unstable. And if there is any simple pole on this, then obviously it is a critically stable system. But if you have two poles, multiple poles on the unit circle, then it is said to be an unstable system. So, right, this is what we can infer from the analysis that we have made so far from the previous class. And now we will see whether the system is stable and what are the various methods to find out stability. So, methods of absolute stability. Methods of absolute stability. In the methods of absolute stability, to determine absolute stability, we have three different methods. They are the Scar-Kohn stability test, Scar-Kohn stability test, the Jury's stability test, and the third one, bilinear transformation, bilinear transformation in combination with the Routh stability criterion. In combination with the Routh stability criterion is what we will be seeing. Right. In this methods of stability, absolute stability, we have Scar-Kohn stability test and Zurich stability test, and these two tests will give us information only about how many number of poles are location of how many number of poles. It will not give us the exact location. The values of the poles will not be given to us. Only thing is, they will only tell us how many poles are lying on the outside of the unit circle, or inside the unit circle, or on the unit circle. But the exact values of the poles will not be given by this Zurich stability test. Right. So this is one important factor which we will have to understand. And we only require whether the system is stable or unstable or limitedly or marginally stable. But we don't require what is the location of poles in the stability analysis, where the poles are lying and all we don't require. Only thing, when we are going to convert or transfer the poles from one place to another, trying to make the system even more stable, we are then going to require the location of the poles. But here in this case, we don't require any location of poles for determining the stability. Only number of poles that are lying inside or outside or on the unit circle will be sufficient for us to determine the stability of the system. Right, the absolute stability of the system. So these two tests, and most importantly, what is the difference between these two is, in the Zurich stability test, the polynomial p of z, all the coefficients a0, a1, A2, so on, An. All these values are real. All these values are real in nature. In this Zurich stability test, we can determine from the real values of the coefficients of the characteristic equation. Whereas this Kirchhoff stability test, you will be having the poles P of Z, the A0, A1, A2, An. All these are, a few of these might be complex in nature. Therefore, computations are more and more difficult in Kirchhoff stability test compared to Zurich stability test. Therefore, we will be discussing only Zurich stability test and most widely used. Zurich stability test is most widely used, most preferable compared to Kirchhoff stability test, because both are solving the same purpose and with less number of computations you can go for Zurich stability test. Therefore, we will be discussing Zurich stability test and the bilinear transformation plus Routh stability criterion in the next part of the lecture. So now let us discuss the Zurich stability test. Now what is the Zurich stability test? It is a method of absolute stability. You can have Zurich stability test, which is a very simple method to find out whether the system is stable or not. First thing we will have to consider is P of Z, which is A0 Z power n, A1 Z power n minus 1, A2 Z power n minus 2 plus An minus 1 Z plus An. Now this is an equation and we are going to consider this P of Z. Now we will have to write down the Zurich stability table. Right, Zurich stability table. Right. In this Zurich stability table, Mr. Zurich has defined in such a way that we will be having the number of rows in one column. Right. Number of rows in one column and Z power n, Z power n minus 1, Z power n minus 2, Z power n minus 3, so on, Z square, Z power 1, Z power 0. Now the coefficients of this Z power of n power n minus 1 so on will be considered here. So first thing that we will have to understand here is we will consider from the coefficients A0, A1, A2, so on, An minus 1, An will be written in the reverse order. So we will write it here as An minus 1, An minus 2, An minus 3, right, and A0, A1, A2, right, and the second row we will be having A0. The reverse order of this is considered A1, A2, A3 and An minus 2, An minus 1, An. Right, the reverse order is considered in this. The third row we will be considering Bn minus 1. Right, where for example let us say Bk is nothing but An, determinant of An, A0, then An minus 1 minus K, K plus 1, where K is 0, 1, 2, so on, n minus 1. Right. So this is considered, or we can say when K is equal to n minus 1, we have Bn minus 1 is equal to An, A0, n minus 1 minus n minus 1 A0 and An. Right. And this goes on up to when K is equal to 0. When K is equal to 0, B0 is equal to B0 is equal to An, A0, An minus 1, A1. Right. So that will be considered. So you can see when k is equal to n minus 1, it is bn minus 1. First value is considered as bn minus 1, right? And you can say an, a0, an. So these two, an, a0 and a0, an. The determinant of that must be written here, bn minus 1. And therefore you can write it like this, bn minus 2, bn minus 3, bn minus 4. And eventually from k is going from 0, 1, 2, so on up to n minus 1, you will be getting all these values. And up to what value you will be having? b0 and b1. You are having only n minus 1 terms in this row. Therefore, and in the fourth row, you will reverse this order. b0, b1, b2, b3, so on, bn minus 2, bn minus 1. Okay, now in the fifth row, we will be obtaining values from, see, we have obtained third row, we will be obtaining values from the previous two rows, and fourth row is obtained from this, and fifth row is obtained from these two values, fifth row is obtained from these two values, where I put it as Cn minus 2, right? And Ck is given as, you can say Ck is obtained from these two rows, so Bn minus 1, B0, okay, Bn minus 1, B0, Bn minus 2 minus K, Bk plus 1, and K is ranging from 0, 1, 2, so on, 0, 1, 2, so on, n minus 2. 0, 1, 2, so on, n minus 2. Here we have b from up to n minus 1, here we have up to n minus 2. Right. So we are having this, therefore C n minus 3, C n minus 4, C n minus 5, so on, C n minus 2. Sorry. C naught. We are having from C naught. Right. We are replacing this order. And therefore, in the sixth row, we will be having C0, C1, C2, C3, Cn minus 2. Now, eventually, we are putting all this, okay, and we need to get the last rows. How many rows we will get? We will be having 2n minus 3 rows. Right, we are having first row, second row, third, fourth, fifth, sixth. And how many number of rows we will be having is depending upon the 2n minus 3 rows. For example, when n is equal to 2, what is 2n minus 3? 2n minus 3 is equal to 4 minus 3 is equal to 1 row. So the last value when n is equal to 2 is 1 row. Therefore, 3 quantity, that is z square plus az square plus bz plus c is equal to 0. This will be the last row. Therefore, a, b, c. You have 3 elements in the last row. Therefore, you can go with that. So, I can say it is 2n minus 1, 2n minus 2, 2n minus 3. Right. We are having such rows. So, the penultimate rows are 2n minus 1, 2n minus 2 and 2n minus 3. So I put it as 2n minus 1 the row. 2n minus 1 the row. I can put it as P3, P2, P1, P0. Right. The previous rows you will be having in such way, and 2n minus 2 it is P0, P1, P2, P3. Where what is Pk? Pk is equal to, right, or you can say Qk, where Pk you can also obtain from the similar equation. Let me consider 2n minus 3, the last row. You can say Q2, Q1, Q0, Q2, Q1, Q1, where Qk is obtained from P3, P0, P3, P0, then P2 minus K, Pk plus 1, and K is from 0, 1, 2. Right, you can understand Q2, when K is equal to 2, Q2 is equal to P3, P0, P0, P3. Determinant. Right, Q2 is obtained from P3, P0, P0, P3. Right, Q1 is obtained from P3, P0, P1, P2. And Q0 is obtained from P3, P0, P2, P1. So, this is our Zurich stability table. Now, with all this in mind, we are going to write down the Zurich stability criterion. With this in mind, we have obtained all these values, and with this in mind, let us see what is Zurich stability criterion. Zurich stability criterion. What is the Zurich stability criterion? If any linear time invariant single input, single output, discrete time control system is characterized by the equation P of z is equal to 0, which is a0 z power n a1 z power n minus 1 plus an minus 1 z plus an. Then we will write this Zurich stability table, and from this, where mod a0 greater than 1. A0 is always greater than 1. You can say mod a0 is greater than 1. Always a0 must be positive, and the remaining values may be positive or negative. Right. Therefore, here the first condition here is you have obtained a0, an, bn minus 1, b0, cn minus 2, c0 and all these values from this Zurich stability test. And here the important thing is mod a0, an is less than a0. Mod an is less than a0. That is the first condition for the system to be stable. Right. For this system to be stable, conditions are first one, mod an less than a0. Second, P of z when z is equal to 1. This is P of z. When z is equal to 1, a0 plus a1 plus so on, this one must be greater than 0. Greater than 0. Right. Third condition is P of z for z is equal to minus 1 must be greater than 0 when n is even, and must be less than 0 when n is odd. Right. So we have these conditions. When n is odd, for an even order polynomial, you have P of z when z is equal to minus 1 should be greater than 0 when n is even, and when n is odd, that is an odd order polynomial, P of z must be less than 0 when z is equal to minus 1. So this is the third condition. And we have the final condition, fourth condition, which is nothing but it is similar to first condition. What is the first condition? Mod an less than a0. But here mod bn minus 1. Mod bn minus 1 must be greater than mod b0. Here we don't have mod. Mod an less than a0. And here mod bn minus 1 greater than mod b0. Mod cn minus 2 must be greater than c0. So on. Mod p3 greater than p0. Mod p3 greater than mod p0. And finally mod q2 greater than mod q0. Mod q2 greater than mod q0. Right. So these are the various 4 different conditions which, if the system satisfies, then the system can be said to be stable according to Zurich stability criterion. So these are the various stability criterion that we have, and let us go with a very small example to determine absolute stability using Zurich stability test. let me leave these conditions here. We will try to follow these conditions in this case. Very small example which we will consider. P of z is equal to z cube minus 1.1 z square minus 0.1 z plus 0.02. This is our example. And determine whether the system is stable with respect to Zuri stability test. Now this is A0. What is A0 for us? 1. A1 minus 1.1. A2 minus 0.1. A3 0.02. Right. And what is the stability condition here? First condition, mod An must be less than, A0 is greater than, is positive. A0 is positive. Right. That is already existing. Now mod An is less than A0. Mod An is this one. That is mod A3 is less than A0. That is 0.02 is less than 1. This first condition is satisfied. Now what is the second condition? Second condition is P of 1. P of z when z is equal to 1, isn't it? Z is equal to 1. That is 1 minus 1.1 minus 0.1 plus 0.02 minus 1.2. Sorry, you can consider this as 0.2. In the question itself, we will have a small change where we are having 0. Right, 1 plus 0.2, 1.2 minus 1.2, you have 0. So P of z when z is equal to 1 is equal to 0. This condition is partly satisfied, but it is equal to 0. When it is equal to, it means that there is at least one pole on the unit circle. Therefore, this will give us, due to this reason, the system might be critically stable. The system might be critically stable. It is only might be critically stable. It is not yet critically stable because we will have to complete the conditions, verifying the conditions. Now, what is the third step we have? P of z when z is equal to minus 1. Here, if it is 0.2 also, it doesn't have any problem in the first condition because 1 is always 0.2 is always less than 1 in the first case, right? So you can have it. Now this is a odd polynomial. When odd polynomial, the value must be less than 0. Let us see if it is less than 0 or not. When z is equal to minus 1, this is cube, so minus 1 minus 1.1 plus 0.1 plus 0.2. Therefore, this is minus 2.1 plus 0.3, it is minus 1.8, which is less than 0. Hence, this condition is also satisfied. Now let us see what are the other conditions that exist for us in this. With the help of this, you can say you are going to draw the table, Zuri stability table, GST. Now this is rho, then z power n, z cube, z square, z power 1, z power 0. The first row is, I will come in the reverse order, 0.2 minus 0.1 minus 1.1 and 1. Second row we have 1 minus 1.1, 0.1, 0.2. And the third row, how many rows we will be having? 2n minus 3, where n is equal to 3. Right, so 6 minus 3, you have only 3 rows, 1, 2, 3. So we are having only 3 rows. 3 rows in the sense you have only 3 different things. And what is this value? Modulus of 0.21, 1, 0.2. 0.2 whole square, 0.4 minus 1, that is minus 0.96. Now what is the next point? 0.21 minus 1.1 and minus 0.1, where we will be having minus 0.02 plus 1.1. So we will be having minus 1.8, sorry 1.8, right. And here what is the other one? Minus 0.1 and minus 1.1. Therefore, we will be having minus 0.22 plus 0.1. Right. So minus 0.12. Minus 0.12 is our condition. Now we can see that in this case Bn, this is Bn, right, 0.2 must be greater than 1, and Q2 must be greater than Q0. This is Q2 and this is Q0, and this is Q2 and Q0, and since this is not satisfying the relationship, then this is an unstable system. Okay, so we are having a limitedly stable system in one case and the other is the stable system. Therefore, we can consider that the conditions here given in the Zurich stability test are all giving us information about how many number of poles are there in the inside of the unit circle, the outside of the unit circle, and on the unit circle. Now let us go for the third Zurich stability test, which is nothing but the bilinear transformation plus Routh stability test. Routh stability test, in the continuous time control systems we have already designed Routh stability test, therefore we need not worry about Routh stability test in this class. Only thing is we need to understand what is bilinear transformation here. This is a very simple transformation that we are transforming all the polynomial equation from z plane to another complex plane, which is w plane, and w is given by, or z is given by w plus 1 by w minus 1, and if you can manipulate this, you will also have w is equal to z plus 1 by z minus 1. So bilinear transformation, you can have these two transformations, right? Once you can convert any p of z, which is a0 z power n, a1 z power n minus 1 plus a2 z power n minus 2 plus so on, plus an minus 1 z plus an. This, if you replace z with w plus 1 by w minus 1, then you will have p of w, or you can say it is nothing but q of w, because it's some other plane you are going to obtain, and you will have the values of some other constants b0, w power n plus b1 w power n minus 1 plus so on, plus bn minus 1 w plus bn. So you are going to get some other polynomial equation if you replace this with, and similarly when you replace w with z plus 1 by z minus 1, you can get back this equation without any problem. That's why it is called a bilinear transformation. You can transfer z plane to w plane, w plane to z plane. But here only in this w plane or bilinear transformation, when bilinear transformation is applied and obtained and converted all the z plane poles and zeros into the w plane, then here you can only find out the absolute stability but not the relative stability. Relative stability cannot be obtained, right? Relative stability cannot be obtained using this bilinear transformation, because in our previous case what we have understood is, in our previous session we are converting s plane values, that is plus j omega s by 2 minus j omega s by 2. This is called the primary step in our which we have studied in our previous lecture, right? All poles and zero, all the values that are lying in the left half of s plane, this is an s plane, right? These are infinite number of poles, and all these poles can be mapped onto the inside of the unit circle. And similarly, we have a complementary strip, infinite number of complementary strips on both sides in the positive and negative directions of the imaginary axis. Right? It means that what we have discussed in our previous class, for every point in the z plane, there are infinite number of points in the s plane. Right? And for every point in the s plane, there is definitely one point in the z plane. That is what we have discussed in the z plane, in the mapping here. But here in our z plane to w plane analysis, what is happening? For every one pole, you have only one. For every one value in the z plane, you have only one value in the w plane. Therefore, it is restricted. As far as the visual representation is concerned, you can say that s plane and w plane are one and the same. But in actual practice, only primary strip is converted into the poles into zeros in the z plane, right? But for every one value in the z plane, there are infinite number of values in the s plane, but there is only one value in the w plane. Therefore, relative stability cannot be obtained in this because there are many number of strips. All the complementary strips are neglected in the w plane, right? So, relative stability is not possible using this bilinear transformation. Only the absolute stability is possible. Now, what is a bilinear transformation and how is it obtained? Using this one. For example, in this bilinear transformation, what are we trying to do? We are trying to just find out what, instead of z, we are replacing it with w plus 1 by w minus 1. And p of z is a0 z power n, a1 z power n minus 1 plus an minus 1 z plus an. Right? And when you are replacing z with w plus 1 by w minus 1, we will be having some other polynomial q of w, and we will be having b0 w power n, b1 w power n minus 1 plus bn minus 1 w plus bn. Or you can simply write how we got this in the sense, you can say a0 w plus 1 by w minus 1 power n plus a1 w plus 1 by w minus 1 n minus 1 plus an minus 1 into w plus 1 by w minus 1 plus an. Right. And if you can get just w minus 1 power n, if you can multiply throughout, then you will have some value which is b0 w n b1 w n minus 1 plus bn minus 1 w plus bn. Right, and this is our w plane. And from this w plane, if you apply the Raoult stability criterion, Raoult stability criterion is similar to again the criteria that we have used in the continuous time control systems for a linear time invariant system. Then those conditions can be applied, and you can find the stability using the Raoult stability test. So what we have discussed, to summarize what we have discussed in this class, we can say that we have understood in what way the location of roots of the characteristic equation give us about the stability of the system, right? And what are the various methods of absolute stability? One is the Square-Cohen stability test, and why we are not going for Square-Cohen stability test compared to Jury stability test we have discussed, and the bilinear transformation plus Raoult stability test, right? So these are the different methods which we can find out, which we can use to obtain the stability analysis of a closed loop system in the z plane.